This is the third episode of my more intuitive model of quantum mechanics. In this episode, I want to talk about electrons around atoms. As before, I'm using two postulates to try to make quantum mechanics more intuitive. First is that quantum objects are instantly reformable wave packets, all part of one thing. And the second postulate is that they might instantly reform when they interact, depending on how much of them is interacting, according to the Born rule, where probability of collapse to region is proportional to the squared amplitude. In the first episode, I talked about these postulates at length, and if you haven't seen that episode, it might be a good idea. Anyways, let's move on. So in these later episodes, I want to talk about how varying the parameters of wave packets gives us interesting quantum phenomena. So in the second episode, I talked about varying the size of a wave packet versus its wavelength, and that gave us the uncertainty principle. In this episode, I want to talk about confining a wave packet. And later on, I'll talk about allowing wave packets to interact and join, which gives us entanglement. But here, we're going to focus on confining wave packets. So you put a negatively charged electron near a positively charged nucleus. What do you expect to happen? Well, they're attracted to each other, and the electron's much lighter, so you'd expect the electron to fall towards the positive nucleus. And you may be expected to go into orbit, but it won't go into orbit because when electrons move in curved paths or they accelerate, they give off energy in the form of photons. So it's losing energy as it moves around the nucleus, so it's just going to spiral in and sort of fall into the nucleus. So this whole idea that electrons orbit is just plain wrong. They don't orbit, and unfortunately this is still taught in schools. A better picture is that the electron is a wave packet attached to the nucleus. Now, it can't enter the nucleus, so it has to basically sit around the nucleus, and it doesn't accelerate around the nucleus because it's sort of attached itself there. Now, the wave envelope is not moving relative to the nucleus, so it's not accelerating, but inside the wave packet is oscillating, and basically it still has kinetic energy because it has a frequency and so on. So the electron packet is not orbiting, it's sort of stuck there, and it's not accelerating, and it's just a standing wave surrounding the nucleus. And most of the time it can't enter the nucleus, but under certain conditions it can. Okay, so often you're shown these sort of diagrams in high school and they're wrong, but what's right about this diagram is that electrons in certain energy states can only get to other energy states by absorbing a photon of just the right frequency and energy. So a very high energy photon will kick the electron right out of the nucleus, but if you want to move it from orbital to orbital, and of course orbital is a terrible name because nothing's orbiting, you have to give it a photon of just the right energy. And when electrons move from excited state down to a lower state, like the ground state, they give off a photon of just a certain frequency. So that's what's right about this, and of course what's wrong is that they are implied to be orbiting, and they're not. If you take something about quantum mechanics in high school, you might see these orbital diagrams for electrons around atoms, and what are these all about? Well, they're often called probability clouds around the nucleus, and that's true. So if you took 1,000 detections of precise locations of where you find the electron around the nucleus, if they're in the ground state, you get a spherical distribution around the nucleus, and if they're in a p state, you'll get these sort of two-lobe distribution of a whole bunch of electrons here and a whole bunch of electrons here, and so on. And for the d state, kind of the same thing. So why do they look like this? What's going on to give us this orbital structure, as it's called, even though orbital is a terrible name? Let's look at it more closely. Since the negative electron is now confined to a region around a nucleus, it's a confined wave packet. And when you confine waves, they start to act kind of like a guitar string. So if you pluck a guitar string, you get a bunch of waves. What they are is standing waves. The ends are fixed, so waves can't exist outside this region. You can get a wave like this, and a wave like this, and a wave like this existing. But these wavelengths have to fit the size of the guitar string, and they must fit the potential well for quantum mechanics. So basically, only certain frequencies and certain wavelengths are allowed, nothing in between, and that's just the way standing waves work. So electrons are forming a standing wave, And if we were to confine electrons to a square potential well like this, you would get waves that look a lot like guitar string waves. And since different frequency means different energy in quantum mechanics, you could get a wave like this, or a wave like this, or a wave like this. And the electron might exist in any of those possible states, but only just sort of one of them at a time. But the electrons are not sitting in a square potential well. They're in a spherical potential well. And spherical potential wells look different, and then the wave behavior is different as well. This is a parabolic potential well, but it shows you, this is a bit different. And so anyways, if you put in a spherical potential well, what do the resulting vibration modes look like? So if you confine an electron to a spherical region, these are the sort of vibrational modes that you would get. And these are animations I got from Wikipedia. So here's the 1s orbital, the 2s orbital, and 3s orbital. Now these are not quite what the vibration modes look like. They're vibrating in 3 dimensions, and this is sort of a slice through that. It's a little more complex than what we're seeing here, but still this gives you a good idea of what's going on. Now, the way they're vibrating is kind of hard to see, so I've included these vibrational modes from drumheads because they're easier to see. So this is the first vibrational mode that you would get, and it's simply kind of going up and down, and this is the more excited state of an electron that you might get, and even a more excited state. Now, all electrons want to be in the 1s orbital. They want to stay there if they can, but there's only 2 that can exist there, and then you've got to go to a higher energy orbital, the 2s. So suppose you have an electron in the 1s state and you make it instantly reform by hitting it with a photon. Where do you expect the electron to collapse to? Well, you'd expect it to probably collapse to somewhere right in the middle, because that's where the amplitude is the biggest. Now, that is where the amplitude is the biggest, but there's a little bit of a mathematical caveat here in that there's 0 volume at the center. So basically, because there's 0 volume at the center, you can't actually detect the electron there because there's kind of no electron there because there's 0 volume. And you go a little bit away from that, that's where the squared amplitude suddenly allows you to detect the electron. So you would expect to be able to detect the electron very close to the nucleus, but not at the nucleus. So this is the 1s probability distribution of where you might detect the electron. Then you have the 2s state. So there's a region right here where basically the amplitude is always 0. And if the amplitude is always 0, there's no possibility of detecting the electron there. You can't make it instantly reform there. And also you can't make it instantly reform right in the middle. So you can detect it right near the middle, right near the center of the nucleus, and you can detect it over here, but never in between because the squared amplitude is 0. And for the 3s state, you've got 2 spots where the squared amplitude is always 0, here and here or so, and you have 3 places where you might detect it. So if you make a whole bunch of detections of an electron in these sort of S states, what do you expect to see? Well, if you do 1,000 detections and you look at it from the outside, you kind of see a spherical distribution around the nucleus. And if you slice through that distribution, there's a region here and a region in the middle for the 2s state where you don't see any detections because the square amplitude is 0 right there. So you kind of have a shell around here and another shell of detections there, and then the 3s state, you kind of get a similar pattern. So that's what's going on with the s orbitals. Now what about the p orbitals? So electrons try to occupy the s orbital if they can, but if they can't, they have to vibrate in a higher energy mode, like the p orbital here. Now you can kind of see what's going on here with the p orbital. It's oscillating like that. It seems to match up to these kind of balloons in the p orbital diagram here. And you can see that the wave envelope for this would match up to these. So if you were to try to detect the electron when it's in a p orbital sort of state, then you would find it maybe here, but where the amplitude is 0 here, you'd never find it. So you can see how these lobes form for the p orbitals. And then we have these other oscillations. This one looks like a d orbital, and this is probably an f. And you can kind of see how we form these sort of balloon-like orbitals, they're called. And of course, orbital is a terrible name because nothing's orbiting. Now, if you were to look at the probability of finding the electron in the 2p state, this red line, you can see that it goes something like this, and that makes sense from what you can see here. So that's how we form these orbitals, and that's what we're talking about. These are wave envelopes for the standing wave of the electron around the nucleus, and you can also translate that into the probability of finding an electron at various locations kind of is given by these wave envelopes. This seems like a good time to talk about electrons in bound states and the uncertainty principle. So electrons around the nucleus have a very definite energy and a definite frequency. This is because you're basically fixing something at both ends, and the wavelength and frequency you're going to get is quite definite because it's a standing wave. So to transition from one state to another, you have to hit it with a photon of just the right energy and frequency to get it up to here, and then this one will emit a photon to drop down to a lower energy level. And so what this does is give you a large uncertainty in your position. So momentum relates to frequency, and if the uncertainty momentum is small, the uncertainty in your position is big. And this is sort of a large wave packet, and you have a sharp distribution for your frequency, but a broad distribution for your positions, and where collapse might occur is over a broad region. If you have a large nucleus with lots of protons, it's going to attract a lot of electrons to it. So how are those electrons going to arrange themselves around the atom? Well, they're all going to try to go to the 1s state, because this is a ground state, and electrons like being at the lowest energy level. But you can only put 2 in there. And the reason has to do with something called spin. So if the electron is spin up, it can occupy it. If it's spin down, it can occupy it. But there's only 2 allowed, and once they occupy the spin up and spin down states, you have to go to the next energy level, which is the 2s. And once that's occupied with 2 electrons, then it's done, and you have to go to the 2p state and then fill up those, and eventually you start filling up electron energy levels around the atom. Now, the reason why you can only put 2 electrons into each orbital is because of the Pauli exclusion principle, which basically states that you can't have an electron, which is a fermion, occupy the exact same state as another one, and that's just one of those rules about quantum mechanics. So helium has a filled up 1s state, and then beryllium has a filled up 1s and 2s state, and you keep occupying these electrons and you keep building up the periodic table. Now, you might think that, oh, well, once you fill up the 1s state, you get helium, so therefore, once you fill up the 2s state, you would get another noble gas that's unreactive like helium, but you don't. You get beryllium, which is quite reactive. You don't get a noble gas like neon until you fill up the 2p states. And once you fill up all those, well, then you get a noble gas. Now, I don't know any intuitive reason for this. And then you have to fill up 3s and 3p, and then you get argon, the next noble gas. So I don't know of any intuitive reason for that, but basically we can predict all the properties of the periodic table mathematically with quantum mechanics, but I can't really give any intuitive reasons for why it behaves the way it does. So what is spin? Well, electrons, protons, and neutrons, they all produce a magnetic field that looks a lot like the magnetic field produced by a spinning ball of charge. And the way you produce magnetic fields is to move charges. And one way you can move charges is to spin them around. However, electrons, protons, and neutrons cannot be spinning in order to produce these things, because a spinning neutron, since it's neutral and has no charge, should not produce a magnetic field if you spin it. So something else is going on in these wave packets to produce this magnetic field. And what it is isn't intuitively clear. Most physicists today regard spin as something fundamental to particles like mass or charge, and it's just something that they have intrinsically. So they all have intrinsic angular momentum for some reason, and there's no real intuitive analogy that I've ever heard of to basically explain why they're producing these magnetic fields, but they do, okay? And how do you produce these things? Well, an electron coming into a magnetic field may have a spin to it or it may not. One possibility is that it could be both spin up and spin down at the same time in what's known as a superposition. So it's spin up and spin down at the same time. But when it hits a magnetic field, it collapses, it instantly reforms to produce either a spin up field or a spin down field. If this is the right sort of magnetic field, the spin up particles which agree with the magnetic field will get deflected upwards, and the spin downs which disagree with the magnetic field will get deflected downwards. And if you remove the magnetic field, these particles will tend to retain their spin and they'll travel along. And if you re-engage the magnetic field, the ones that were spin up will all be 100% spin up after they pass through it. So but it's a state that they collapse to, and something about the wave packet changes, but what's changing isn't all that clear from an intuitive sense. So if these spin helps produce magnetism in things like iron and nickel, as well as the PDF orbitals. And fermions, which are electrons, protons, and neutrons, they have what's known as type 1/2 spin. And bosons, like photons, they have what's known as integer spin, so 0, 1, 2 sort of thing. And this is has to do with the mathematics of quantum mechanics. And spin's a very important concept for the mathematics of quantum mechanics, and goes beyond just producing magnetic fields, as I've described here. How does chemical bonding work in quantum mechanics? Well, we can basically understand that you've got these potential wells, and the electrons are standing waves vibrating in these potential wells. And they always want to get to a lower energy state. They always want to get to the ground state if they can. So if you put another atom right next to it, you modify the shape of this potential well. You basically make it wider, and that allows an electron that was forming a standing wave here to drop down in energy a bit and form a new standing wave. And once it does that, a chemical bond is formed. And that's basically how chemical bonding works at an intuitive level. Tunneling is an important aspect of quantum mechanics, where you have a partially confined wave packet existing both inside and outside of a potential barrier. And here's a simple wave packet that I've drawn existing both inside and outside of this potential barrier. And I'm bombarding it with all these other quantum wave packets. And once in a while, it's going to instantly reform because of these wave packets hitting it. And most of the time, it'll instantly reform inside the potential barrier and it won't escape. But once in a while, it'll interact with something outside of the potential barrier and escape just like that. And this is basically how radioactivity works. So particles can tunnel out of unstable nuclei and you get radioactivity. Also, it's how fusion works, and two things fuse together, they tunnel into each other, and how semiconductors work. Tunneling is important for semiconductors as well. So this is a very widespread and important quantum phenomenon. And I'd just like to acknowledge where I got the images and animations that I didn't make up myself.